Okay, cool. We are live. So welcome everyone to this live science session on a Tuesday. Carlos, Nick, and myself are going to be exploring spinal graphs. So yeah, Carlos, can you tell us what is a spinal graph?
Yes. All right. Hello, everyone. So today I wanted to go a bit deeper and discuss a bit further this concept of spinal graph, which we introduced last week as a means of encoding what formerly we called edge symmetry. Now, more properly, we should probably be calling edge type, which essentially amounts to the sort of data structure that a hyper edge in a hypergraph is encoding or is sort of capturing. So I thought today we could do a couple of things. So we could have a first half, roughly, since we have roughly 2 hours allocated for this meeting. We could spend about an hour just conceptually coming back to some of the points that we made last week. Last week, there was a lot of things to present, and there was sort of my first sort of overall presentation of this new hypergraph philosophy that we're trying to formalize. Today, I want to focus much more on spinal graphs, and so I wanted to come back to some of those points more conceptually first, just with whiteboard discussion. And then afterwards, maybe Nick can share some notebook and we can do some live coding on possibly the canonicalization simply by encoding the complete graphs or whatever. Some points of discussion in the conceptual part might inform what we do in the second part, but does that sound like a plan?
Yeah, that sounds great.
Sure. Okay. So let me share my whiteboard here, and I'm probably going to turn off my camera because I'll go horizontal, and I don't think a view of my chin constantly is going to be that appealing. So I'm just gonna turn off my camera momentarily, and I'm gonna show. Sorry. Let me know if this shows appropriately in the screen.
Yeah, it's showing. I'm just gonna switch to a good size.
So
cool. Okay, that's good.
You can have your faces here. Great. Let me just. Why is Zoom prioritizing my turned off camera over Nick? That makes no sense.
It's probably pinned. From our side, it looks fine.
Yeah. No. Yeah. I just want to have a nice view of you guys while I speak. So I have some nice, beautiful faces showing in my screen at the same time. Okay. So, all right. So what are spinal graphs? So just as a very brief recap, I hope you can still hear me well.
Yeah.
A bit of noise of changing positions. Okay. So the essential idea of spinal graphs, maybe I'll just draw it here on the side. If we think of a hypergraph generally, without doing all the conceptual recap that we did last week, you typically want to think of some sort of elements that are given, your nodes, and then some relational information between them. And the relational information here, what we mean is, to be precise exactly today. And so in general, typically, you would think of things like bags, things that are just some relation. So it's kind of a unfeatured triangle between them. There could be directed edges, something that has like a, like a line between two nodes that has an orientation. It could be something like a cycle where these things are sort of included in some kind of cycle that is rotating in a specific direction. This is filled in. There can be several data structures, and these all make sense. The most common ones in the literature are the likes of bags, so where you just have collections of nodes sort of in a set without any order. Tuples, which are essentially just chains of directed edges, things that look like that. All with the entity, right? So this is the same edge. And many-to-many, so a generalization of the directed graph, which is basically, you have many nodes as input, and they all sort of get sent as a whole to many other. So maybe you can write a bit more clearly, something like this. These all get sent to other many, for example, 3 here, right? So these are the most typical data structures in the literature. These are very simple data structures. So part of our motivation was to cover in our hypergraph formalism and functionality was to cover all these data structures and more, and anything in between that would be reasonable. So our proposal is this idea of, or my proposal, at least last week, was this idea of spinal graphs to encode these kinds of data structures. So there's a few things that I wanted to discuss with you guys about data structures. So first of all, we might want to consider whether disconnected spinal. So okay, so what is a spinal graph? So I should mention this more generally, just to recap. Okay, so what is a spinal graph? So spinal graph is a, as the name suggests, is a graph structure on a set of nodes that is intended to capture the specific data type that the hyperedge is meant to be. So, for example, in the case of a tuple, so in this particular example, which we have a tuple, the data structure is explicit there. So the spinal graph is sort of explicit there. I mean, some people won't use a graph to represent that. They would say, oh, that's actually just a list, right? Where you have your nodes in some kind of ordered list, and that's your hyperedge. Well, of course, that is equivalent to saying, well, there's a well-defined successor function, and so you can represent the application of the successor function by some directed edges, and so you can essentially sort of do away with all the sort of circumstantial information about the tuple and just keep the graph, the basic graphic structure behind it. So similarly, when you have a bag, you might want to say, this is a bag structure. You might want to say, I have no specific order. I have no specific information of what node comes before what. And so if you're interested in some kind of sequentiality information about those nodes, then you should be thinking that all possible permutations of these are possible, right? So, or are allowed in this way. So you would like to write something like, those 5 edges are all, fully connected with all the, I mean, there's a lot of things here, right? Yeah, and there and so on, right? So that's the complete graph on those 5 nodes that were in the bag. So the idea, of course, being that you wanted to somehow express only with a directed graph, with a perhaps simple connected directed graph, to be more specific, you wanted to express that sort of data structure. So that's what we discussed last week. If you want to see much more detail on examples, I just refer to last week's live stream recording. But today, I wanted to a little bit expand on what the expressive possibilities are, just by virtue of what these things are. First comment is about connectedness of the graphs. So something that I just glossed over last time and we didn't discuss at all, but it's actually quite important. And maybe there is something to this that helps us understand it and helps settle some of the discussions that we had last week. Should we want connected or disconnected spinal graphs? I think we probably want connected spinal graphs generally. The reason being that if we're going to consider, so the reason being that the main motivation to use spinal graphs to begin with, someone might be wondering, why the hell do you try to put this information into a graphic structure where there's no problem with having some kind of permutation information or some kind of head that specifies an internal permutation symmetry or something like that? Well, the reason is that for practical purposes, when running hypergraph algorithms, most of the time you want something like a head that is traversing your node set, that is somehow moving along your nodes, and most of the time you want to specify a path between nodes in a specific way. So if you can provide path information in a very compact and minimalistic manner, well, that's some work that's already been done for us, instead of basically just giving us a set of nodes and saying this is, you can permute them as you will, right? So here I will say something a bit more specific here, just conceptually as a summary, is that if you tell me that these 3 nodes, remember that they will have unique IDs. Let me just give them names for now, so that is clear. You tell them that they are in a bag, right? And you tell me that this is an edge in your hypergraph, and some algorithm arrives at this edge and needs to somehow check something for all edges, for all vertices, something like whatever the degree, and there's maybe some coloring going on because there's some kind of Wastephaler-Lehmann procedure for isomorphism or whatever it is, you want to check every single node in this edge. So if you want to do that, and your information is not held as a list, or if it's held as a list, it's just given as a specific list. So maybe you have this as an ordered list in your computer or in your data structure as 1, 2, 3, but this is a bag. Then you need to supply the information that actually you can permute, and it's 1 to 3, but it's also all S3 symmetries are included. So I'll represent that as a group and some kind of arrow to represent that is sort of acting on the permutation. So meaning that the list 1 to 3 represents the same object as the list 1, 2, 1, 3, which in turn represents the same object as 1, 3, 2, and so on, right? And so the problem you have here is that if you begin at number 1 and you want to follow a path, and basically a path meaning that you want to check what happens on 2, you want to get some data from 2, maybe a label information and a degree information there. There's no immediate way to navigate to either 2 or 3 in a way that is sort of specified. Right? I mean, this is a very small example. You say, well, you just choose a path, but there's no instruction sort of natively that tells you go to 2, go to 3. You'd have to say something like, move one step in the list and then check if that is connected or not according to your permutation symmetry, blah blah blah. However, if instead of having the specification of the symmetry of the bag, we had the specification of a graphic structure in this, and we said that all permutations are allowed, so that means that we have a complete directed graph on these 3 vertices, right? 1, 2, 3. So that's a bad idea. So 1, 2, 3. And you have something like this, which basically, in all directions. Then if I am placed at 1, this directed graph tells me that I have 2 possible paths that I can follow. I can go to 2 or I can go to 3. And that's it. That's all the outgoing paths from 1. Then if I'm at 2, it tells me that I can go to 1 or I can go to 3, and so on, right? So in terms of the efficiency of just the navigational information, it is much more direct, it's much more compact. Of course, I can recover the symmetry group by, for example, considering either automorphisms of the graph, right? If you think of the graph automorphisms that are actually sort of preserving the directedness of the graph, then you would get S3. Those are the symmetries of that graph very, very explicitly, right? And further, maybe we want to not only consider automorphisms in abstract, but we might want to consider specifically paths or flows, which are collections of paths with certain properties that behave in that way. So, for example, here, any homotopy group, either on 1 or 2 or 3, is going to have the S3 structure, right? It's going to reflect the S3 structure, basically, because you can imagine you can have a path that goes all along 1 to 3 in a cycle, or you can have a path that goes back and forth from 1 and 2, for example. So those are the generators of cyclic permutations, and the other is the generator of the transposition, right? So anyway, so that's a summary of what spinal graphs are and why we care about them, or at least why I thought there could be an interesting alternative for algorithms and for particular processes. Again, I'm not saying these are the sort of the panacea and it's going to be the final solution to everything. It's just a new way to encode information that gives us a lot of expressive power, hopefully, as we will discuss in a moment, without having to encode symmetry explicitly and by remaining fully graphical. That's perhaps the in my opinion, the greatest advantage to this is that we can have information that is purely graphic. So it just allows us to, so it just demands us to specify what it means to be a directed graph and what it means to be a collection of nodes, which is super simple. And that, in principle, will give us the entire tower of hypergraph types and mixed types and all that stuff that is currently a complicated problem to deal with in general hypergraph algorithms. So, are any sort of high-level questions, conceptual questions at this point, or should I?
One quick question on this, because I thought about this after the last stream. So this spinal graph encoding of this 3-vertex hyper edge or bag that we have here. So just to test my understanding here of the concept, how would the spinal graph look for a 3 vertices with undirected binary edges between them versus one hyper edge?
Yeah, give me a second. So there's a big important difference here. So I'm just tidying up the picture just for clarity. So this is sort of the symmetry root, and this is the spinal root. So those are actually two different situations in reality, because this thing here, this would look, I mean, you have to remember that this is a single edge, right? So if you have 3 edges here, you would have 3 spinal graphs. So technically you would have like, this will turn into something that looks like this, right? So 3 edges with 3 bags, right? Each edge has a bag, and then each bag has its spine with all the permutations inside, right?
Okay.
Right. Now, if you have something that is an undirected ternary edge here, right? Then this will turn into a single bag around the 3, right? So something that looks like that, and with the same kind of spine. So what's important here is that these spines actually, they know the bag they're in, right? So it's a graph that knows the bag that it's in, and in some sense it's either colored or labeled by the bag or something like that, right?
Got it. Cool.
Right. Anything else before I go into the sort of not so comfortable questions, perhaps? Okay, so the first question is about connectivity. In my opinion, because you want, okay, let me put it clearly. The main role of a spinal graph is to encode navigational information. By navigational, I really mean something like a head that is reading node by node in sort of a computational process that checks for information at every node, and does some kind of minimal computation at every node. So connectedness might be something. So full connectedness on an edge might be important if, for some reason, we want algorithms that actually take some form of complete specification only by doing graph paths, right? So only by doing walks in graphs, right? If we for some reason wanted to completely constrain ourselves to doing walks on directed graphs as our sort of algorithmic, engine or part of our engine, then I think disconnected spinal graphs would probably be problematic. I don't have a specific example in mind why this might be necessarily problematic, but it's actually very closely connected to another point that I have at the end here. Actually, maybe discuss it first, which is the idea of connectedness degree. So it's not just the idea. So there's a question that is, I think, easier to dismiss, at least for now, which is the fact of being fully or not connected. So this is just a yes or no thing. It's, are you connected or not? Meaning, can you find a topological single component among all your nodes or not? I think conceptually, at this point, to me, it makes more sense that yes, they have to be just all in a single connected component, but I don't see immediately why this would be necessarily problematic, but conceptually makes more sense. Now, what it's clear is that
what about the directed edges? Are those actually common? Those will be disconnected, right? If I'm not mistaken.
Which one, sir?
The directed edges, when you have just two sides, like, I know, like bipartite graph or something, so that you can like the sides.
You mean a graph that looks like this?
Not a graph, but like if you just have edges, if you have a single edge, right, and you can partition it in 2 pieces, and you can permute all the pieces independently.
You mean many to many, for example?
Yes.
like something that might look like this, right?
They're just not connected together, right? I
What do you
mean,
mean?
if you just do like a ternary, like we had this example last time. If you have an edge with 4 vertices and you just can swap 2 pairs of them.
Yes.
Right? So this is like a directed edge in a way. Not just directed, but in a way it's like bipartitioned into 2 pieces.
Yeah. So these 3 examples in the connectedness degree image, that's what I'm trying to show here. I'm trying to even do a smaller example than 4. I think it's enough to take 3 to illustrate your point, which is that, clearly, according to my current understanding of spinal graphs, that these 3 examples seem to be something that separates. So these are bipartite graphs, right? Like I have one that has 1 input and 2 outputs, like clearly, right? In all 3, but they are different directed graphs, right? Like in all 3, I can see that 1, 2, and 3. Let me call this 1. These are 1. This is 2, 3, and this.
I think the first one, the first one is bipartite graph.
Okay, sure. Yes. So, yeah, my point is, you have a sort of an initial node in all this, right? Like you have a node that has no heads. It has no edge head, right? Which you can identify, and if it's similarly in many to many, right? If you specify a few nodes that just have outgoing edges, right? Those are easy to identify as sort of input and to be sort of initial nodes, sort of things that whatever, like source nodes. And then if you have other collections of nodes that only have incoming edges, then those are easy to identify as target nodes, right?
Yeah.
So what I'm saying is that in these 3 cases, there's a clear input node. A clear input node, which is 1, just by construction. But it seems that the output of let me call them ABC, just for reference, A, B, C. In A, we seem to have a collection of 2 nodes as output. In B, we seem to have a tuple of 2 nodes as output. And in C, we seem to have a bag of 2 nodes as output. So I'm not so worried about B compared to A or B compared to C. Those seem like reasonable differences. But A compared to C is kind of uncomfortable or confusing to me at the moment. Because, I mean, in some sense, if I think of it mathematically, it makes me a bit uncomfortable because 2 and 3 are clearly these are dangling edges. They don't have any structure, so you can permute them. There's no sense of order between 2 and 3. But in some sense, computationally, if I tell you that 2 and 3 are just distinct nodes and there is no connectedness information between them, that is actually different from saying there is some connectivity information between them that is either unidirectional from 2 to 3 or is bidirectional from 2 to 3, 3 to 2, right? So to me, it seems that this actually represents a richer spectrum of data structure than just good old mathematical sets or mathematical tuples in some sense, because A to me represents just the absence of connectivity information between nodes. Then B represents, the total order kind of information between nodes, just directed structure between them. And C represents the bag structure of connectivity, which means like all possible permutations are allowed between them. So undirected edge, so to speak. So, but yeah, I don't know. What do you think about that?
I mean, isn't that the case for all monoergodic graphs?
Say it again.
Wouldn't that be the same case for all non-ergodic graphs? Like, it's not going to reach every vertex starting from any one point, following the directedness of the edges. So in other words, B and C are orthogotic and A is non-orthogotic, because it'll terminate if you just take a head following each path. So, well, not terminate, like it'll get stuck basically. Like it won't, like if you flow from, in the case of A, if you flow from 1 to 2, you'll never reach 3.
Correct.
Yeah. Whereas in the other cases, you will always reach every vertex, regardless of where you start.
Well, that's not true, right? Because, I mean, if you start at 2 or 3, you never reach 1 in any of them.
Sorry, A and C is. Sorry, that arrow on the B, was a little bit round. Okay.
Sorry.
Yeah, they don't. They're not circulating. Okay. None of them are orthogotic. My apologies. Okay.
Yeah. So, no, but yeah, exactly. So that's what I said in the beginning, that the fact that you can single out node 1 in this topological manner, in this, I don't even want to know, I mean, it's topological, but it's more specifically sort of path topological, right? Like you say that 1 is singled out because it's the only node that only has outgoing edges, right? No path can land into it. Only path can come out. So that distinguishes 1, and I think that's why, and this is pure intuition now. I don't have good mathematical or stronger computational arguments to tell you that those need to be the input nodes in a more composition. Because I mean, for them to be input, you need some sense of compositionality. Perhaps this I didn't mention last time, but it's quite important that these things need to be compositional. And that's something probably I completely neglected to mention last time. But these things should be able to somehow paste together nicely, right? Like if I the main point being, if I have an edge floating around with this kind of ID 1, 2, and I have another edge floating around here with this kind of ID 2, 3, it's clear that I can actually concatenate these two things, and I can make an edge that has the ID 1, 2, 3 in this direction, right? 1, 2, 3, and and it preserves somehow the nature of the edges, right? So this is a directed edge. This is a directed edge. This is a directed edge, right? In this sense, I mean, I don't think this is paramount to consider when just defining the spinal graphs, but it's something that it is at the back of my mind when considering these things. Oops. And
isn't there a generalized version of the data in A that you could say 2 has connected its information to 3 via 1? In other words, there's information that goes both ways. Like maybe there's
you can certainly relate 2 and 3 by saying that they have a common parent, right? And you can define this sort of parenthood relation in nodes, and then certainly you can. I mean, that's another way to characterize what I was trying to say, which was, 2 and 3 are disconnected nodes. So you can define this sort of parenthood relation, which is not connectedness in a graph sense, but it is precisely what the category theorists would call a span, in the presence of a span in the diagram, in the graph, which is precisely that shape, right? 1 goes to 1 to goes to 2 or 3, it could go to many, and so however many it goes to, they are all related, and the relation is naturally symmetric, right? And it's naturally reflexive in some sense, if you want, and so it has that. But anyway, I think that the point here that I was trying to answer to Nick is that, to me, it seems clear that node 1 and nodes 2 and 3, in all cases, can be somehow be given 2 different status, right? Somehow, like 1 is clearly an input node in the sense that it's a source node, and 2 and 3 are different. They are all different among ABC in each example, but they are clearly all different from 1 in a purely topological sense. So I will be inclined to think that this is doing something like, placing 1, in this sort of spot and then saying 1 is at this spot of the edge, and then there's some kind of directed information, and then here I have 2 and 3, and 2 and 3 have different kind of relational information between them in both cases. I have, the first case, no information. Second case, there's a tuple information. Third case, there's a bag information between them, right? Like there's a tuple grouping, no grouping. Okay, let me put it this way. It's like saying 2 and 3 are not grouped in any way under this connectivity pattern. In the second case, they are connected by a tuple, and in the third case, they are connected by a bag. So that's sort of what I had in mind. So maybe let's try to work out the example that you had last time and see it again, just to. So did you have so it's important to know whether you had an idea of a data structure that you wanted to represent, or a graph that you wonder what data structure represents. Which one it was? You remember?
Well, just a graph. It's because you insisted on for the spinal graph to be connected. I just remember that particular one that we considered last time when we have disconnected one.
Oh, disconnected?
Yeah, it was disconnected. You just have, well, just draw like 4 vertices and connect only pairs. Just make, right? Okay. We were considering it as a type of symmetry, right? You can swap 1 and 2 and 3 and 4, or 1, 3 and 2 and 4. Doesn't matter.
Yeah.
Right, so it's like a disconnected one.
Yeah. Of course, this connects to the question about connectivity in general. Yeah, I mean, the reason why, as I said, why I don't like connectivity is that if some algorithm lands us on edge 1, for example, if we're going to run some kind of graph path subroutine, so to speak, when we reach that edge and we try to like reach and maybe find some kind of Hamiltonian path on the edge, so that we visit all the edges to do something like canonical renaming or like counting degrees or whatever it is, this graph will not help, right? Because it will make us think that 1, 2, and 3 and 4 are not connected. And I think the point perhaps is more than the fact that the graphs are connected. Maybe I need to be. Yeah, it's more like there exist nodes. I mean, maybe this is always true, and I'm just making a trivial statement, but at least it's trivially true, so I'm not super worried. There exist nodes from which paths exist that allow you to reach every other node on the graph. I think that's always true for a connected graph. I think I'm making a very trivial statement. But I mean, they are clearly true for all the graphs that I've drawn, like in the examples, right? Like if you have a tree, you go to the highest root, or the deepest root, I guess, and then you can reach, with paths from that root, you can reach any other node in the graph. In a cycle, it doesn't matter where you are because they're all symmetrical. In many-to-many, you go to any source node, and then you can reach any other source or any. But that's assuming.
Are you saying that there is always a vertex that from which there is a path to any other vertex in any graph?
No. That's stronger than no. That's not true. Obviously, for all graphs, that's not true for all graphs. But I'm saying that maybe that's what we want for spinal graphs. So it's a stronger condition than actually being connected, right? Precisely because of this idea that you want.
What do we want? It's okay. Well, what's the definition of what we want? What
I think
we want and what we not?
Yeah, I think wanting the existence of a node from which paths will take you to every other node in the graph, existence of at least one, node with that property.
Okay.
That's,
Can I try an idea? If you move this up a bit, I want to draw something that I just thought of. It's like a subspinal graph. So say you have like that example here where you've got this thing, and then you said there's one edge here or one edge there. Okay, those should be in the middle, but whatever. Let me do that quick. Okay. So there's one there and there's one here. So what if everything contains like a type of spinal graph, but it's not complete, or like it's not like realized? And what happens is you can start at any arbitrary vertex. Like let's say here, you always follow the connected path first, and then when there's no more connectedness, you take the second order back, and now you're back here. Now because you started at where you've ended, you've run out of the first iteration, so you need to iterate on like a second traveling. You need to, like this one got left here basically. So now you've used up your one because you're back at the first vertex. Now you're going to use two, and then two travels along this connected branch and ends up here. It can't do anything else, so the head travels back along the unconnected one. So now you've used up two, so you end up with like something like that.
Yeah, no, that sounds like an interesting way to sort of program the behavior of a head moving along directed graphs. But I think the question here is a bit more general in some sense. That, I mean, bringing up this question at the conceptual level, at the whiteboard level, for me is a way to ask from you guys, where do you see the utility, or where do you see the potential for this to help in defining some algorithms? And like, I mean, I understand that the disconnected graphs, in principle, I mean, from a mathematical point of view, my mind is very quickly telling me, just take disconnected graphs, it's no problem. Just take, a bag of nodes. Is any directed graph structure, the category of directed graphs is perfectly well defined. It's a perfectly fine category. You don't need to constrain in any artificial way. Just take simple directed graphs on a bag of nodes. That's a spine. Like that, my mathematical mind is really strongly telling me to do that, right? But then I land on this kind of examples of like disconnected graphs or connected but with different degrees that don't neatly correspond to data structures that are usually expressed in hypergraph literature, or even in our own Packlet and our understanding of hypergraphs. Maybe that's just irrelevant, because maybe only a subset of directed graphs express what we want, and the others are there just sitting around as other things that don't have any meaning for us, which is fine. But which in some sense will always be the case if we restrict to a subcategory of directed graphs. That will always be other graphs that are not, that we could consider but are not considering, and they're just not encoding stuff that we think is relevant, and we're not naming, and we're not sort of including in our algorithms and whatnot. But yeah. Can
we do some more examples maybe that will help form the intuition, like like very simple hypergraphs and the spinal encoding for each one.
Yeah. So then you mean going, because that's the thing, like the direction here matters a lot, right? So you want to consider like specific kinds of hyperedges, and then that we express them with a directed graph, right? With a spine.
With the spinal graph, encoding of the edge. Okay.
Yeah.
So there's one spinal graph for each edge, basically, is what you're saying. And those spinal graphs are not. So there's not a spinal graph representation of a hypergraph. It's a set of spinal graphs.
Yes. The spinal graph really is just a efficient, or intended to be efficient, encoding of sequential information within an edge, right? That's sort of the idea. So, I mean, I can I can even go back to the, I don't know, I feel like, I mean, I can just draw them again. Just maybe draw
Wait, so
them
is the question the other way around? Are you saying if these are the spinal graphs, what is the
Yes.
what is the hyper edge supposed to look like? Is that
Yes, exactly. That's the question here.
okay.
Yeah. So that's mostly what I'm asking here. That, you know, if I were to give you this kinds of graphs, a disconnected one, I mean, in principle, you know, there's it just seems a little bit odd. I mean, and Nick, I think your question boils down to the core question that I'm asking here, which is, what is the difference between A, B, C in those diagrams, right? Like, which is this gradation between no connectivity information between nodes, some connectivity information between nodes, and full connectivity information between nodes. That's kind of like what spinal graphs allow you to express, but I'm not really sure how to understand the difference between A and C necessarily.
But well, what is your context that you're trying to answer this question in? Right, obviously it's like different graphs. What is the context in order to even distinguish them? Well,
the context is that
graphs are just representations.
No, I understand. So I have natural data structure representations for A, B, C here. I mean, at least for B and C. And let me just write them down. So, you know, in here, the data structure representation of B will be, you know, one is sending. So one is the source. So I have a tuple where one is here, and then it has a tuple structure because everything is a target in this sense, right? And that tuple is 2, 3, right? So I see that data structure from B. From C, what I see is, again, tuple 1 with something, because that subgraph is the same. You know, 1 has the same topology around it. But now instead of seeing 2, 3, I see a bag of 2 and 3 because there's full symmetry between them. So 2 and 3 as a bag. I mean,
Okay.
I think I used.
So these spinal graphs are supposed to encode any arbitrary combination of directed and undirected edges and hyper edges, right? At the same time.
Say it again.
The spinal graphs are supposed to be able to encode the edges of a hypergraph that has directed or undirected edges and or hyper edges. Like it's supposed to be able to have the combination of any of those things in one encoding.
Yeah, one encoding per edge.
Yeah. So
yeah.
Isn't A then just a hypergraph that? Oh, oops, sorry. Let me make some space at the bottom. So isn't A then just? Okay, isn't A then just the hyper edge of a ternary edge with directedness information inside the hyper edge like that? So in other words, there's a directionality to the hyper edge.
Sure, but what is the difference between that and C? That's the question.
Okay, C. Okay, well then in C, see there's like an ambiguity here basically. Interesting.
Why don't you just put like 2 and 3 in their individual compartments?
Maybe it's just that. Maybe there's
in their slots. You mean, Nick? You mean in the tuple slots?
Yeah.
But why the order? There's no sense in which 2 comes first and 3, right?
And then put a bag around that.
But then, sure. But like what is the difference between that and C?
The difference between like an element and a singleton set. I don't know. That's the difference.
Oh, okay. I see what you mean. So you mean that here, wait.
Curly brace, then like a
curly brace 3.
In the curly brace, and each 2 and 3 in their individual braces.
Yeah.
Like that, right?
Yeah, I think it doesn't matter whether those are bags or not.
Yeah. If it's unary, there's only bag. There's no. Yeah, but I mean, I agree with you that this is definitely a reasonable option. But I guess
because in the Hyper-Edge version, this remains a Hyper-Edge. So in a way, 2 and 3 has more information related to it in terms of undirectedness, whereas in A, the directedness of like there's some kind of incoming flow here and here, and an outgoing flow here is easier to represent than this, where these can go both ways basically. Because like there's no flow because one only has outwards direction. There's no flow from 2 or 3 back to 1, but between them there is information. So it would be weird. Like in order to represent this properly, there needs to be a normal graphical way of showing hypergraphs with flow information of each vertex. Like this has an outward flow, and then these don't have any flow in C case. In the A case, it's something more like this, where this has an outward flow, this has an inward, and this is an inward, something like that.
Yeah. I'm just thinking now, Nick. Yeah, James, I think that's morally correct, actually.
Morally correct.
No, yeah. I mean, it's relevant. I think it's a good characterization.
Not even wrong.
No. That's not what I mean. That's not. No. That's a good characterization. But I am thinking that maybe. And let me see if this is wrong. My mind is very slow when thinking about this stuff. Is it true that if we could just delete all bidirectional edges in all the examples, that can be right, because then you will end up with disconnected components.
The point here is that if you want to represent all of those spinal graphs as some kind of nested groupings of directed things and tuples and bags, right?
Yeah.
You can do it similarly. That you just have to require probably so that you have your bags and tuples can iterate, but for example, you can arbitrarily postulate that whenever you have bags of bags, they flatten out, right? For example, so that your A, I would still rewrite it as each 2 and 3 would be like individual singleton tuples, not bags. So that's like, otherwise it seems like already a bag of 2 and 3. It's not very different. But in this way, you would iterate tuple bag, right? Otherwise, they would just flatten. Each bag would flatten inside each another bag, and tuple also kind of is allowed to be flattened inside another tuple. But if you just nest it, maybe you can differentiate those different cases. Essentially, each because you can also think of each individual vertex as just a singleton tuple. You just don't write it. But maybe you should, unless it's in a bag.
You mean if I had a vertex just like this, and that's my edge, and then you mean that I should do something like this?
Well, if it's actually have this loop, then yeah, maybe it is a singleton tuple, right? Well, yeah. Now we should answer like maybe we should draw like a D version when you have this kind of loops around 2 and 3. If you want to also distinguish those cases.
Okay. Yeah. Yeah, I think we should be aware that these are really meant to be the spines of edges, and so nesting can happen naturally at the hypergraph level, right? The nesting structure is what a hypergraph allows you to do, right? Because that's what I mean. Hypergraph allows you to go sort of wide, but also deep, right? Like you can have a higher order edge and you could put things inside, sort of like this idea of bags. Bags are sets, therefore there's this partial order of sets of being subsets and so on, right? So I think I would be happy if we have a consensus on what is a good encoding of just flat data structures. So not zero nestedness, right? Like for only one level of nesting, which probably means that we need to somehow constrain what directed graphs we allow. But because then the hypergraph structure is what allows us to do nesting, right? If I want to nest, I can just say, you know, I have a directed, for the kind of nestings that we have here. James, can I write?
Yeah, I'll clear it. Oh, you want to keep it or must I clear it?
I'm just gonna move a little.
Okay, sure. Yeah, it's gonna stick on the screen, so I'll clear it.
Yeah, thanks. So for example, if I wanted to create this data structure, right? I might want to just say, I have a directed edge. Yeah, just draw the same thing. I have a directed edge. And then I have a, you know, whichever encoding, whatever this means, right? This is a ternary edge.
Mm-hmm.
But then I also have this, right?
Mm.
And so in this sense, the bags, just the bag projection just looks like this, right? So the bag is a subset, like the bag of the directed edge is a subset. And this really, like the structure in 2.3 is directed in the sense that it's the target of one, or they are the target of one. But in terms of a data structure, it is a substructure, it's a subset of the 1, 2, 3 as a whole. Like the point of my definition of edges as bag plus spine inside means that there's always a well-defined sense in which edges can be subsumed by other edges, right? So that's kind of the point, that we don't. I think nestedness is natural once you assume that. So we don't really need to be granular enough with, because I really think directed graphs are not expressive enough to do nesting, like generally. So if, for example, if I want to express, like, how the hell do I express this kind of thing, right? Like this tuple, right? In mathematics, actually, these things are all equivalent, right? In some sense. Because of the associativity property of the Kuratowski pairs, right? These things are defined to be, in fact, I mean, this object over here is actually defined to be as the equivalence between these two objects, right? In the usual definition of tuples in mathematics.
So the definition of tuple has associativity, but do we know that associativity exists in what we're trying to do?
Well, but that's what I'm trying to say, that if you try to distinguish between these three things with just directed graphs, it feels like you're going to, like, let me put it this way. A nested tuple as a data structure, I think, I don't know, I haven't thought a lot about this over my life, but I think a nested tuple should be different from a tuple, just computationally speaking.
Oh, I see. Okay.
But mathematically, the tuple is just a tuple, right? It's just like n tuple is well defined, and it's basically just an ordered list of elements, of n elements, right? Computationally speaking. But obviously, computationally speaking, a list with lists nested inside is a different thing. I mean, sure, you can flatten the list and you can get one single longer tuple, but that's a different story, right? In some sense, like technically, you do have a different structure. And my fear is that these structures are not entirely obvious in terms of in terms of expressive power, right? Somehow. So, yeah, I mean,
you're talking about tuples now specifically.
I'm talking about tuples specifically because this is basically what directed graphs give us in some sense.
So why don't we just use tuples instead?
No, tuples is, I mean,
that's a joke.
and that's what we're already using. That's already what the language is using. So that would be the the trivial solution of no use of anything that's been presented as an alternative, which might be the right thing to do. I'm not saying we should definitely use spinal graphs, but they need to be shown that they're not useful because they seem more compact than permutation groups because of the amount of information, and they are graphs, so we can use a lot of the graph functionality that is very well known already.
So do tuples like a type of a higher order? Like is it like is it something on top of set theory? Like, does tuples exist within set theory? Like, is it some kind of like additional constraints on top of sets?
Yeah, they are constructed from sets. Like normally in mathematics, the Kuratowski construction is that the tuple of two elements AB is defined as the set of A and the set of AB. Right, so it's kind of a clever construction where it's just a collection of two sets, and so you by definition you have this property which is crucial, right? Sorry, A. Right. And I think you can.
What about B by itself? Why is B not allowed to be by itself? In the top
What
one.
do you mean not allowed?
So there's an A in the curly brackets and there's AB in the curly brackets. Why can it not just be B in a curly bracket after that?
Because then it's fully symmetric and then you did nothing.
Okay.
I mean, the point of a tuple is that sets don't have order, right? Sets don't have any internal order.
Okay, I see.
That's what a tuple is. A tuple is just it's a totally ordered set, right? That's what a tuple is. And so you can simply at the level of set theory, you can do this trick. You can do it in other ways. Like there are other ways to axiomatize this stuff. But one way to axiomatize tuples is just to do that. I don't think this is very relevant for us, to be honest, because we are operating in a different setting in a way. Like we want to have computational systems that deal with graphs, generally, hypergraphs, and so on. So the whole point here is that it might be enough to have a system that deals with sets, which is the bags, the specification of a collection of things, which is, that's inescapable in some sense. If we are doing computation with discrete elements, that's always going to be the case. And my claim here is that instead of accounting for the jungle and the zoology of combinatorial species that you get, with this sort of factorial explosion of possibilities as you increase in arity, instead of dealing with that complexity, we just say, well, because in reality, we just need to know how to navigate our edges internally when doing some algorithms. As long as we have something that captures things uniquely, we are content with just a graph, just some smaller amount of information that characterizes the behavior. And so that's why we're trying to understand like how different graphs might be encoding the same thing or not, and how to understand.
What if you bring back the edge places idea and then put spinal graphs as add extra nodes for the edges in the spinal graph?
But how would it help? This whole question is, the whole problem is confined to a single edge. There's no sense of there being a hypergraph around it. Like there's really so far the problem is fully confined to a single edge. We just want to understand that if the problem is that we don't have a question to answer. Like we are just setting things out. We are not trying to solve a problem. Like that's the issue, right? Like we have a broad problem of, can we have a general way to encode edge types that include undirected, directed, many-to-many, cyclic, and all these kinds in a sort of parsimonious and elegant way that is also computationally efficient and that can pull from all these algorithms in graphs and so on. And as Nick said last time, that this is sort of the same philosophy that we've been running with other, like currently hypergraph isomorphism. What it does is it turns hypergraphs into graphs, and then those are checked for isomorphism in a specific way. So this is very similar to that, right? It's like taking some hypergraph information, turn it into graph information, or in some formal sense, having the graph information as part of the definition of the object, and then your checks for pattern matching, isomorphism, this kinds of difficult things, you actually reduce to directed graph isomorphism problems, which are much more better understood, right? And we have a lot more powerful algorithms that sort of out of the box we can use. So before we get into how to do that for hypergraphs, which is just collections of hyperedges, the point is, do we actually believe that it is enough to, or these spinal graphs do the job? Because so far Nick and I thought of permutations. So basically you specify a tuple, so your edge is a tuple together with a set of generators of permutations that give you the redundant information of that tuple. So if the edge is just actually a tuple, you have no extra information. You'll just have that collection of names, of IDs, and that's the exact distribution of the tuple. So meaning, in this case, right, if you have this kind of situation where, just delete this one, right? And this is 1, 2, 3. In this case, the symmetry encoding is just list 1, 2, and 3 with just the empty, not the empty group, but the identity group, right? So there's nothing to change. It's just 1 to 3 doesn't move. That's the data structure, right? But because you want to encode everything that has maybe 1 and 2 can be permuted, but not 3. Maybe 1, 2, and 3 can cycle around. Maybe 1, 2, and 3 have no order whatsoever, and there's just like a bag. Like you want to encode all this rich set of types, of sort of structure types. Then we thought, yeah, we'll throw some permutation generators as part of sort of like the metadata or the sort of tag data of the edge, and that will be enough, right? But the problem was that, this is perfectly fine. There's nothing wrong with that just for its own. The problem was when we tried to implement algorithms that did canonicalization, it was a complete mess, right? Like when we tried to canonicalize arbitrary symmetry, like arbitrary permutations, it was just a mess. Like we didn't know how to start. At least I don't think we really got very far. I don't know if Nick, you had a different sense of why we got stuck.
I wouldn't say we got stuck. We just saturate. Well, because as I said, we don't have a problem to solve. That's the only reason we get stuck. Not because we're stuck for some, because we don't have some bad type of the edge, and it leads to some kind of mess. I'm not sure.
What is canonicalization?
We did have a problem that if we wanted to, for example, consider symmetric, cyclic, and tuple, like simultaneously, it will be, and we wouldn't have. We would have to separate the hypergraph, just consider it as different hypergraphs, then canonicalize them separately, and then put them together again, right?
Something like that.
Yeah. So in the process, basically, adding the complexity of finding the edge types where the specification of a hypergraph is just a collection of edges where the edge type can be specified within the edge information, right? So it's really like a bunch of edges, each with their own symmetry information or edge type information. So you would have to first parse the entire hypergraph, separate it in the edge types, then canonicalize each of them, then put it back together and so on, which is fine. That's not a problem. But it felt like, at least I couldn't imagine a systematic way of doing this, right? Like just writing down like a pen and paper algorithm. I tried.
You just described the systematic way of doing it. I don't understand.
No, but once, okay, no, but forget about but then you incur in the explosion of the symmetry types, right? You incur in the explosion of, like, the moment you have arity 4, 5, 6 and higher, the amount of possible symmetry types is just insane, right? Because it's not just all the permutations.
It's never larger than the amount of edges anyway. It's still going to be more efficient to, if you canonicalize in each symmetry separately, it's always going to be more efficient to separate by pieces. There can be more pieces than the actual hyperedges. So any partition of the hypergraph into sub-hypergraphs that you can canonicalize is always better.
Mm-hmm.
So why is it an explosion?
Okay, no, but right. So an explosion, if you had big hypergraphs where you didn't know which edge symmetries you have. Obviously, if you have your data like declared to be in certain symmetry types, then there's no problem. But if you have a big data set and you don't know exactly which edges have which symmetry, then you have to search for symmetries, right?
Well, that's a completely different problem from the canonicalization.
Sure.
Searching symmetry, it's like some inherent symmetry of the hyperedge inferred by global hypergraph connectedness or what? What does it even mean to search for symmetry?
Well, in the sense that, I mean, you would only get, I mean, you're right. I mean, the at most you have the number of edges to check. I agree with that. But there might be situations where just checking all edges once for symmetry and then performing some canonicalization is going to be quite expensive because of the number of edges and the possible partial symmetries. If instead you had an algorithm that just took all the edges.
Well, exactly. The smaller the hypergraph, the simpler the canonicalization should be.
Yeah.
So how is it would be faster to consider all hypergraph at once instead of any partitioning and individual symmetries?
No. I'm not saying it would. I mean, partitioning symmetries is fine. I never said that was the issue. Like that's not the problem. What I'm saying is that sometimes just getting the partition in the first place might be very expensive already. So you might add like if you have a canonicalization that cares about partitioning into types, it might be more expensive in itself. I mean, it's just an intuition here, but my point is more about this spinal graph approach seems to just only care about the same sort of object, which is a spinal graph, which is a directed graph that
Basically, okay. When we had a symmetry, when we have a hypergraph with individual symmetries, we also kind of have a single object. It's just the way we decided it are quite arbitrarily, I would say, just partitioned by symmetry only. That's how canonicalization should be defined.
Yes.
But it shouldn't be the case. It's like right.
But I think the problem was more the isomorphism of symmetry, right? Like to check the two edges have the same symmetry, right? This is not obvious from a permutation generator description of the symmetry.
Well, it is obvious. You just permute it in all possible ways and explode it. You make a bigger hypergraph, right? We already discussed. Just if you have symmetric edge, you just replace it with all its symmetries and make a directed hyperedge, a hypergraph, global directed hypergraph. That's what you're supposed to canonicalize. So that's the only problem we had. That it's like when you do it, maybe it's going to become too difficult or something.
Yeah, exactly.
But in principle, I don't understand how this would solve this problem.
Well, because
Spinal graph is just particularly maybe the exact same thing as just replacing a single hyperedge with more structure.
Well, the difference, I think, is that you might end up only checking directed graph isomorphism for each edge symmetry check, instead of generating all the possible permutations as new edges. You have one single directed graph. If you have an efficient directed graph isomorphism algorithm to check, right, you don't have to generate all permutations of anything. You just say count number of nodes. If they're not the same, they're not the same. If they are the same, just check graph isomorphism on them, and that's it. So I'm black boxing the entire permutation problem of generating and potentially exploding combinatorially and so on to directed graph isomorphism. I'm sure that there's instances where this is not more efficient than the combinatorial explosion because of the particulars of how things generate. But I think generally it seems easier. It seems cleaner in a sense, right?
Perhaps. I'm not sure. It's just, if you want to answer this question, definitely you have to actually compare it.
Sure, I agree.
On some example, do some actual study of what, okay, we have two ways to canonicalize hypergraphs.
Yeah.
Which one makes the most sense and which one is most efficient for particular purpose?
And I completely agree. I'm not trying to argue that there is some mathematical result that is guaranteeing that this is better. But what I'm suggesting here is that, to me, there are two things that spinal graphs do better than generating this thing you call global tuple hypergraph with all the possible permutations. And the two things are, first, the one that I just mentioned, that I can, instead of generating what could be a big, potentially, for sure, big combinatorial explosion in the case of undirected hypergraphs, which is a case that we absolutely want to consider. That is a big combinatorial explosion that's going to happen. Like the moment we consider, like, not even very big hypergraphs of RET 6, 7, 8, whatever, like it's just very big. Just to consider all the hypergraphs that are, like, for each edge, it's like hundreds and hundreds, thousands of edges in new hypergraphs, right? It's just a lot. So the difference is that's one, that I can reduce that to simply checking directly one directed graph to one directed graph that has like around. So Sam Rodke actually had this comment on the Discord the other day that was interesting. So the number of edges in a complete directed graph for an undirected edge is n times n minus 1, right? Because that's the complete graph. So n nodes times n minus 1, which is all the other nodes that have a. So that's the number of undirected edges between them. So 2 times that is the number of directed edges in that. So that's for large n, that's a much smaller number than n factorial, or twice n factorial, which is what you get with full symmetry of the edges. So that's one intuitive way to, like, just look at two formulas that quantitatively tell you that in general it's going to be a smaller thing to preserve.
Can you write those formulas here quickly, just so we can visualize it?
Yeah. So this is argument one for why I think spinal graphs are easier. And this is actually Sam Rodke, our community member, who's the one that was actually bringing this up. So if you have n nodes, you have an n node bag, right? Let me represent this 3. The number of directed edges in the complete graph is given by 2 times n minus 1. So this is the complete. Let me just call it complete spine. right? So in the case of
there's two
there's
times.
2 times because of the
3 times 2 in the end. That
Oh,
equates
you
to
already counted.
6.
Both directions.
oh wait. So
Just 10 times n minus 1 without 2.
oh yeah, that's right. Yeah. It's even better. Some sense. Yeah, because from each edge you draw n minus 1 directed edges to the others. Yeah, that's right. So that's the number of edges in the complete spine. Now the number of edges in the the number of permutations, or the number of permutation tuples is n factorial, right? Which in this case happens to be the same, of course, in n equals 3, but for large n, this is a considerable difference, right? Because n factorial is, just for everyone's benefit, n times n minus 1 times n minus 2.
Well, it's true that there's less edges. It's still not obvious to me that the canonicalization of the spinal graph would actually canonicalize the hypergraph.
I agree. But this is why I said this is the first reason why I think that's why it's an intuitive sort of reason still. I mean, it's based on some concrete math, but it's still intuitive. The second reason is that this allows you to do just completely primitive edge-to-edge comparisons. You don't have to, you don't care whether you have done this parsing about symmetry, you don't care about labels or anything. You can just, look at your labels, look at your directed graph, your spinal graph, and then you can just do whatever graph algorithms that you need to, whatever graph processing that you have to do on those things primitively. Like if you need to probe for some property that needs something a bit more holistic, then you might want to check for automorphisms of those things, or like actual isomorphism or partial matchings and things like that. But you might want just simpler checks and just say, okay, can I find a path that contains the same label twice? Because if not, then I already know they are not the same thing. So it can be like much more direct in this way, where your objects really are just edges and collections of edges. That's hypergraphs. And because they are made of the same stuff, because they're just collections of things connected by some directed graph inside. You don't have to care about what they're called, and then when the permutation group cares about names of the elements, because that's how you see the permutations and so on. Like, I don't know, I feel like that gives you a more direct edge-to-edge comparison. The other thing generates a bunch of objects, right? Like permutations just generate a lot of things. You suddenly have to check many things, right? That's mostly my second argument, that regardless of cardinalities, regardless of like how the quantities seem to scale for like efficiency or computational complexity eventually, the second argument to me is that if the whole point of having the partial permutation groups acting on your tuples generate all the possible permutations and these sort of global hypergraphs that are tuple hypergraphs themselves, and then you can canonicalize them and then do some kind of equivalencing between them. The problem is that in doing so, you're doing a many-to-many relations constantly in distributed locations in your hypergraphs. It seems to me much more complicated and less clean than the fact that if your edges really are bag plus spine, then you can just reduce to a one-to-one comparison all the time. You don't have to generate anything from them. It's like they contain all the information atomically in a graph, right? So again, I completely agree with you. We should do some basic examples and like compare efficiency. Absolutely. Ultimately, that's the scientific way to do it. I completely agree. That's how we should do it. But at least you agree that it's not obvious that one is better than the other, right?
Yeah.
Okay, then we're on the same page.
In the bottom example here with the factorial, is that is that the total number of possible edges that could exist between those three vertices?
So it's it's a total. If you represent your edge as a tuple, and your edge is an undirected edge, that's all the possible tuples that result from permutations, from distinct permutations of your node names.
Undirected only.
Yeah. This is the argument is for undirected because it's the one that has the most symmetry, so to speak. Right, it's the one that has the most redundancy in our systems, right? Like, because I mean, in Mathematica in particular, we're gonna code with lists, right? So these things, but the thing is, Mathematica already has very powerful graph objects. I mean, these are primitive objects in Mathematica. That perhaps is a third appendix argument for my interest in using graphs, is that graphs are already a primitive Mathematica object. I mean, maybe that's irrelevant. Like that's not super important to me, but yeah, that's kind of the point. That instead of
instead of what?
No. Instead of, I was just going to reinstate that instead of going after lists and permuting lists and manipulating lists to do hypergraph processing, we sort of switched to a mentality where we are just manipulating graphs, performing on graphs and rewriting graphs and so on, which is kind of what we do in some sense, more philosophically.
So in this example with the three vertices, don't the numbers come out to 6 in both cases?
Yeah. N equals 3 is the same. Like there's no advantage in it, but as I said, this is for large N. It's like large N. It only becomes relevant for large N. I mean, this is the point about efficiency. I mean, these formulas on the screen are only for the case of only for the case of comparing amounts of data. Like if you have a undirected hyperedge of size n, in Nick's approach of the global hypergraph, you would generate n factorial different tuple hyperedges. There are actual lists in your language that encode the exact same object. So that n factorial, when n is small, it's not large. It doesn't look impressive. But as n grows, that it really explodes. And the alternative is really just scaling with n squared, which is much better, right?
Where do you scale with n squared?
Well, n times n minus 1.
But there's going to be a spinal graph for each edge.
No. It's just a single node, a single edge all the time. So you take a single edge. The fact that the edge is undirected, it means that if it contains n nodes, and you put your edge as a list with permutation properties, you're going to have, in the undirected case, you're going to have n factorial lists that are distinct in your language but represent the same edge, right? But with the spinal graph approach, you have a data structure which is unique, as is your edge. So that's already, in my opinion, an advantage. The fact there's a unique graph representing a unique edge, and the amount of data elements in it, the amount of directed edges within the graph, the spinal graph, is of size n times n minus 1.
So it's like it's like an edge embedding space, but how do you attribute the specific spinal graph to specific vertices then? Where do you store that information?
No, that's primitive information. That's the point. Like in the permutation case, because it's undirected, you feel like there's no information, but actually there is information. There's information that you say the SN group is acting fully in all entries of your list, right? You have the information that all permutations are allowed. So you have and that's very efficient to encode if you only care about that edge atomically. That's why we started that way. That's why we had that approach initially, right? We said, oh yeah, we just encode some partial group actions, and that's it. Like that's enough. You know, that we don't need to care. Like some partial generators of permutations, we are done. Now the problem is that in the simplest case, in some sense, which is the undirected hypergraph case, that approach in practice, in order to use our own system, our own algorithms, leads to this idea of the global hypergraph that Nick's talking about, where we generate all the possible tuple hypergraphs that have no symmetry whatsoever that represent the same hypergraph. And so you can exchange hypergraph for hyper edge in what I just said, and that applies to every single edge individually, right? Because really a hypergraph is just a collection of hyper edges, so you can reduce it to a single hyper edge. So the argument at the hyper edge level is this: you have n factorial permutations in the undirected case, or a single object, a graph, with n minus 1 times n edges on it. That's the sort of two alternatives that are competing here. And to me, it seems very intuitive that this is going to be better. But of course, we should get numbers on this. We should get, you know, a hypergraph isomorphism that checks undirected for like order 6, 7, or whatever, and one that just checks for spine isomorphism instead of. I mean, intuitively, it just seems that it's going to be like, I don't know, the amount of it would have to be measured. I don't know, but because maybe graph isomorphism is very expensive, you know. Who knows? Yeah. Anyway.
Is there a way to compare two hypermatrices very efficiently for smaller tensors inside like a larger tensor, like to see like if there's a tensor that fits within it very easily?
Wait, what do you mean?
Like if we can say that a hypergraph can be encoded in a large hypermatrix. Sorry, jeez.
Matrix, yeah.
Then if we're trying to like identify specific edges in that large hypermatrix, that like global hypermatrix, wouldn't that just be like a smaller hypermatrix that's identical to a piece of that larger hypermatrix? Like it's kind of like a block inside of the much bigger block.
No, the size of the sort of the dimensions of the hypermatrices assigned to each of these global hypergraphs will all be the same. But effectively, they will have entries in different positions. So there will be like scrambles of the same tensors, because the size of the hypergraphs don't change. Right? You're not altering the arities of the edges or the total number of.
But the nodes will be different, right? Like if number of nodes. Like say for example.
No. They will be the same. It will be the same. Everything will be the same. Like the number, like the actual cardinalities are always preserved. The only thing that is not preserved is how you distribute them in data structures. So, like the number of elements in a undirected edge is 3. The number of elements in a list is 3. But in a list, you care about the order they come in, and in an undirected edge, you don't. But the number of elements is always the same.
Okay, maybe I'm thinking about a different question. Like one of the questions we mentioned on the last stream was, I don't know if it was on the stream, but we're trying to compare how frameworks can do certain things. And one of the challenges at the moment is like, if you have a hypermatrix, like a large hypermatrix, and you want to count the number of ternary edges that exist in that larger structure, it's kind of difficult. Or at least like, let's say, let's say how many hyper edges are there of arity 4 in this large hypergraph structure? That's like kind of like one of the things where efficiency matters and the ability to even be able to run that search matters. So what I was thinking is I was trying to see if there was an encoding, like if there's a hypermatrix, like if there was systems that just used hypermatrices or tensors to kind of do that search already.
I mean, it might be that turning your data, your hypergraph data into hypermatrix data and exploiting some existing algorithms for tensors might be relevant. But that's as far as I can see, because I mean, in a way, in order to like when you like one of the problems that we have is sequentializing the edges themselves, right? Like that's, I mean, not one of the problems. I would say that is the problem. The fact that we need some sort of sequentialization of edges, because at the end of the day, we need to consider them in our language as a sequence. And by the way, Nick, I think this is a bit of a change in mentality there. Like if you really take to heart the fact that spinal graphs are a good encoding of data structures, you might just do away with the idea altogether that the information in an edge needs any sort of list structure attached to it, right? Because if it really is represented by a graph, then that's the structure, right? Like it's not like it's a list that then you have to quotient by some permutations because of redundancy, but it really is like atomically, it's just the graph. That's sort of the socket.
We still need to contain, to store the hyperedge itself in the list.
Yeah, the bag itself, sure. But what I mean is that there is a bag and there is a graph, but there's no list, right? In a more sort of computer data structure sort of language. Yeah. Anyway, but what I was saying, James, is that the problem, because we're trying to sequentialize stuff, hypermatrix only is defined when you sequentialize the whole thing, right? Like you need to sequentialize the entire node set, and then once you have that, then then it's easy to just go ahead and do it. I think that just kind of, I mean, in some sense, you don't care in that sequentialization. Any sequentialization is going to give you a hypermatrix that faithfully captures the hypergraph. But encoding symmetry with hypermatrices again is difficult because a 3-tuple has a hypermatrix that with a single one and all zeros, right? A tuple of 3 elements has hypergraph that's a single hyperedge, has a hypermatrix that has a single one in the corresponding entry of the tuple and zeros everywhere else.
Like a 3-dimensional hypermatrix to me.
Yeah. The hypermatrix, the 3x3x3 hypermatrix of the hypergraph 1, 2, 3 has where 1, 2, 3 is a tuple 1, 2, 3, has a single one in the position 1, 2, 3 and zeros everywhere else, right? Because the hypermatrix considers all the positions like 1, 1, 1, 1, 1, 2, 1, 2, 3, 3. It has all the positions. So that's that. Now, if you had an undirected hypergraph, right? So with 1, 2, 3, the bag 1, 2, 3, then suddenly you have 6 ones in your hypermatrix. Right? Your hypermatrix happens to be symmetric with respect to permutations, right? Now, the problem in using hypermatrix, the reason why we have just discarded the hypermatrices, basically, maybe Nick, you can correct me, but my understanding of this is that that hypermatrix, the one that has 6 ones, equals formally the algebraic sum of 6 hypermatrices that have that each correspond to the tuple hypergraphs of that order. Like the 1, 2, 3 hypergraph is 1 plus the 2, 1, 3 hypergraph plus the 3, 2, 1 hypergraph plus, and so on. The 6 of them, right? Like you sum them over and you get the symmetric one. That is very weird because, I mean, you can distinguish by just adding hypermatrices. You just forget what kind of structure you had in the first place. I mean, it kind of algebraically recovers this idea of the global hypergraph that Nick was referring to, where you add them all together and, those they give you the one of the undirected one. So there's some neat correspondence there with the sort of global hypergraph construction. of generating all the permutations of the edges. But if you want to actually use the hypermatrix algebra and manipulate hypermatrices in a sort of an algebraic sense, they become extremely inefficient, in my opinion, because you can't really distinguish. You can really distinguish between like what two separate hypergraphs are. You know, you need to label your entries and things like that, which then becomes very cumbersome. It's like, why do you even use hypermatrices for that? Like, it's not like hypermatrices, I think, are much more like, yeah, I don't know. I think they are more efficient to basically considering multi-hypergraphs on the same set of nodes and sort of considering families of multi-hypergraphs that you are interpreting as some kind of data that can evolve, right? And because the reason I say multi-hypergraphs on the same set of nodes is that, you know, hypermatrices, then we tend to think of them as more or less always of the same dimension, right? Like when we do algebra with them, they don't like spontaneously change dimensions, right? Like we can consider them of different dimensions and combine many different dimensions together. But once we are combining them, they're sort of like blocked objects, like they are stable when they are operated. And that corresponds intuitively to, or more graphically, I guess, to having a constant set of nodes and then populating them with multi-hypergraphs on top. And you know, that's in some situations, the hypermatrix algebra might be bringing up some properties. In other cases, it just obscures better, more than it helps. And so for this particular case where we are actually trying to, I don't know, encode the foundation of the hypergraph system, resorting to hypermatrices that are even more demanding in terms of sequential information, not just inside of an hypermatrix, but actually globally for the entire node set, that's just super artificial, right? It's like, why would I, you know, if you have a big hypergraph with like thousands of nodes, like why should you care to actually sequentially list every single node one after the other when you already are assuming that each node has its unique ID, and having the hypergraph data means that you have the relational information between the unique IDs, but not necessarily, yeah.
Yeah, it depends on the search and the computation you're trying to do. So in other words, if you maximize the data and the search is very efficient, then the total computational time can be smaller. Or if you somehow manage to compress it, but it's harder to calculate, then you could end up with the same amount of computational time. It kind of depends. It's like in machine learning, you either have the training or the inference. Depends where you want to place the complexity.
Yeah.
It's
no,
like
in this case, yeah, it's more like, because this is the whole discussion that we're having here, right? Like the fact that there's no good sense in which, you know, in this diagrams down here, like in which 2 and 3, whether they come one before the other, we are trying to just add bits of information to keep track of that without needing to like parse the whole thing. Like obviously these names are deceiving. These are just unique IDs. These are not 1, 2, or 3, right?
Yeah,
just unique IDs. So having unique IDs, and by the way, because we are going to rewrite, like this is the thing, we should remember, we are going to rewrite this stuff, right? We need to have a very consistent way of updating this information. This perhaps is really the third argument that I want to add. This is not like the Wolfram language argument. It's not really an argument. But the third argument that I would add to spinal graphs is that because we are looking to build rewriting formalism on top of this system, the formalism needs to very naturally know how to rewrite. It needs to know with very small specification and very little information just how to rewrite. If my specification of what an edge is a directed graph, then I have no questions, right? Like I will know left side of a, like input side of a rule and output side of a rule. I will know exactly what is going on if I sort of write the full spinal graphs in both sides. But if I'm writing permutation information of like lists, like you end up with thinking, okay, so new permutations of these and so on. Like it abstractly makes less sense, right? In a mathematical sense, like you're updating the groups themselves. What is being formally rewritten here? But if it's all graphical information all the way to the bottom, right? All the way down, I think it makes the rewriting much easier, because then hypergraph rewriting just really becomes subset specification and directed graph rewriting, right? Together with some context with like labels and whatnot. Like obviously that part is a bit more sophisticated, but in some sense it's kind of parallel to whether you're doing graphs or permutation groups. But yeah, that's perhaps another important thing to bring up before like doing some tests. So before actually we run out of time, because I know that James has limited time. Nick, do you have a good idea how to test one versus the other? Just to like, what would be a good test?
Well, nothing specific. Just do some random hypergraphs of hierarchy.
Okay. So something like, but would you test for something like hypergraph isomorphism, or
just canonicalization?
Canonicalization. Okay.
I don't care about whether there is a morphic, just how fast it canonicalizes, so whether it's actually correct.
Yeah, but that's the same thing, actually. So yeah. I mean, if you have canonicalization, then isomorphism is direct, right? It's just.
Yeah. We have like two canonicalizations. One is more combinatoric, one just directly do stuff with the hyperedges. Another one convert to the graph, exploding all the undirected ones. Well, even the combinatoric one is also explodes one, or multiplies all the hyperedge based on the permutations. And this one is based to, instead of replace a hyperedge with a bunch of directed edges, replace it with a spinal graph, do the canonicalization of the spinal graph, and then group the new vertices again, and do the canonicalization of the hyperedges, of the new hyperedges.
Mm-hmm. So,
by some kind of sort. I'm not sure, maybe just lexicographic sort of is sufficient.
Do you agree with this? Wait, I'm gonna write tuples as just brackets. Would you say that there are 4 tuple hypergraphs that emerge from this?
Perhaps, yeah. Should
Okay.
be 4. Actually, maybe more, because you can pin. Technically, your sets also flip.
Okay, because you. Oh wow, you're also okay. Well, that's more. So actually, because everything is list, that's right. You're correct. In the end, everything is a list. So these lists, and then, yeah, and then the swaps right here.
Yeah.
Okay. So this will be permuted. Let me call it permutation, right? And with the spine. You get this. And you get this. And make it a bit bigger. And of course, I'm assuming here that that a graph is a primitive object, which for Wolfram language programming should be fine, right?
Sure. Not sure what do you mean by that.
Well, I don't know. Like, if I am considering all the lists here, should I consider the edge lists of the spinal graph? Like, because then we are doing something quite like.
No, it's just different ways to make a graph at the end. At the end, you just have different ways of making a graph. Just spinal graph is not unique, right? So like maybe like many hypergraphs, different symmetries make a different spine and can make the same spinal graph. The point is that you canonicalize the spinal graph, and then you also do the grouping of the canonical spinal graph, because we remember all the hyperedges, and then we canonicalize the grouping, and that's the complete canonicalization. So that's the difference in the algorithm. In the permutations, you don't actually have all the permutations. You still, it's like you don't have this other 4. It's like technically just this, if you want to list all equivalent hyperedges, all equivalent hypergraphs, that's what we are doing. What would be all the equivalent hypergraphs as a list to that particular one on the left. But all that matters is just how you convert this hypergraph into a list, into a graph. Right, usually we just do, because those are undirected edges, we convert AB to 2 directed edges, to AB and BA. Do same for the BC, right? In general, if it was a ternary hyperedge, we maybe make some arbitrary vertex associated to that hyperedge, right? That's how we make a graph, and we canonicalize that. Then we remove all the edge-related vertices and convert back to a hypergraph. Yeah, so it's like the only problem, I think, it's like pretty technical problem, is because your spinal, because we can't really canonicalize multigraphs again. The same problem as we had before.
But they are labeled, right?
What do you mean? Just multigraphs in general, we can't generalize. If you have the same edge twice.
Oh. Why not?
That's just the limitation of the algorithm that Wolfram language has. That's
okay.
I think it still doesn't support mixed. Need to check. Just check quick.
But I want to understand something you said. So you said that I get many different spinal graphs, but I don't see how. Like, the spinal graph is unique. The list of tuples is not unique. But the spinal graph
is unique for the given hypergraph. I'm saying that
sure.
that there could be another hypergraph with the same spinal graph.
Of course, yes. But then they would be isomorphic.
No, not necessarily. So I can make a ternary hypergraph with the same spinal graph. It just depends on the symmetry that I choose. Right? Or the property of the edge.
No, because because if you had a ternary one with a symmetry that you want to express like that, right? Which I totally understand, that in principle you can do. I know what you're saying, right? You want some kind of like ternary symmetry that's kind of skew in this side, but whatever, symmetrical on the other two or something, so that the spinal graph of this looks exactly like that, right? I understand. So
yeah,
right.
But what I'm saying that the spinal graph,
it's not the same. It's not the same because this is labeled by a single one.
No, I don't consider labels. We don't canonicalize based on labels. It's just a post-processing of the graph canonicalization procedure.
Oh yeah, but I'm not talking. Okay, fine. I see, but wait, but no, that's the problem. So maybe that's why we're not understanding each other here. You need a container for your like in your list canonicalization, in the permutation approach, you're putting brackets around A and B. So you somehow know that A and B are a single structure, a single edge, just because you're putting brackets around it, right? So you need to put brackets around edges of directed graphs.
Yeah, I have the brackets there. It's just it's not what I'm canonicalizing when I'm canonicalizing the spinal graph. I'm canonicalizing the graph without labels, and then I know the brackets. I take this canonicalization, all the vertex maps between the old vertex to new vertex, right? And then I just wrap them with brackets again. That's the only thing I can do.
Wait. Say that again. I want to understand what you meant.
I don't have labels when I do the canonicalization of the graph. I just have the graph structure, right? Just there's no labeled graph canonicalization algorithm.
Wait.
Okay.
I understand, but okay. That's I think where we were missing each other, because the assumption is that you cannot, like, obviously if you flatten the graph, I completely see your point that you're gonna get different hypergraphs with not similar, but with equal spinal graphs. Then it will fail. Like, I don't think that would work at all. Colored directed graphs, and that's what
that's not what I migrate. I can't distinguish this hypergraph by canonicalizing spinal graphs, even though they look the same.
Yeah.
Based on labels.
Yes.
Right. But that's fine.
Okay. Yeah. So what's?
I don't know. That was your problem. I was just bringing up the multigraphs, not just the problem was multigraphs, not as the problem.
But if they are labeled, then they are not really multi in some sense, right?
No, you can have an actual multi-spinal graph, right? If you have multiple edges.
You can, but as I said, but if it's labeled, it is.
But you can't canonicalize it labeled.
Why not?
Well, you do have an algorithm that canonicalizes multigraphs, labeled or not?
I mean, not off the top of my head, obviously, but
time check. I need to leave in 2 minutes.
Yeah.
Well, that's just the problem of whether we can reuse fast canonization procedure of the Wolfram language. Just like very technical.
Okay. Yeah.
Specific example. If we want to use that, we can't use it as soon as we have multigraphs.
Okay.
Right? That's why we have like this two slow methods for canonicalizing hypergraphs. The one that converts to graph may be faster, but it will fail as soon as we have conversion to the graph that has multi-edges.
Multi-edges, yeah.
And the one that is like works, but it's very slow.
Okay.
That's it.
Okay. Yeah.
Kind of like the story of all computer science.
Yeah, pretty much. Yeah, Nick, do you have a like another 20 minutes to just chat after the live stream, just so I have some takeaways that I can do?
Yeah, and statements for problems for next time. Like, where do we go from here in terms of framing? What is the question we need answers for for the next stream?
Well, I think Nick put it quite succinctly. I think that we need to see just generate take some high RT hypergraphs, do a canonicalization via whatever we already did, or some permutation approach, and then some other approach based on spinal graphs, and just directly compare how fast they are.
Yep.
I mean, does that sound like reasonable?
Sounds very practical.
Yeah.
Okay, until next time then. Thanks everyone for tuning in. Hope you learned something about graphs today and factorials. That was Yeah, I finally figured out what a factorial is, so that was useful for me. Okay, great. Thanks everyone. See you next time.
All right, everyone.
Bye.
Thank you. Bye.